Okay, so the original video was cut off short, so I want to record this real quick beforehand. So obviously we talk about transformers, but we started off with a good old linear layer. So what is that? So if we have, say, we'll go ahead and do the good old housing prices, so we can represent uh, like a house as a vector of its features. So, say we represent it as, or say we look at the features, I don't know, number of floors, and then a number of bedrooms, and then I don't know, we'll say material and location, whatever, some quantitative amounts, and you can represent this as a vector, or a four-dimensional vector. We'll just say it's 1, 2, 5, and I don't know, -1, because why not? And then what you do is so what a linear layer does, or a single, say, neuron, which is what that's called, and a linear layer will take a linear combination of all the input features. So this node will be computed by this weighted sum of features. So it'll be 1 times w1 plus 2 times w2. So you just like follow the uh, the lines, and those are the weights that you multiply by. Plus 5 times w3, and then that'll be minus 1 times w4. And wherever these weights are, this will be one number. And if this looks familiar, if you've taken linear algebra, then this is just a dot product between the input vector and the weight vectors. As interesting as that, or what this kind of represents, is it trying to like pick out the certain features to learn something about the input data. But you actually have a bunch of these, so you have multiple of these. They're all connected. Draw the weights. There, it's a mess. So you actually have 4 different. I'll go ahead and draw a 5th. That way it's not equal, the input and the output. So you actually have 5 linear combinations that you do, and this can be represented as a matrix multiplication, where you take a 4-dimensional input vector. So this will be our original features. So I'll draw it a little bit better. So this will be like number of floors as the top one, and then number of bedrooms as the second, material, and then location as the bottom one. And then it'll be 1, 2, 5, and -1. So this is just our feature vector. And then you pass that through a linear layer, which is just represented as a matrix multiplication, which is a 4 by 5 matrix. And then you get some output matrix, or some output vector, which has 5 parts to it. And this first part is this node right here, which is just the weighted sum that I showed before. And if you do this a bunch of times, then you can have a bunch of nodes. They connect to each other, or they connect to each other. So you have multiple layers of this. Then you can get like the predicted price of this house, and that's just how a linear layer works. And that's what we went over at the beginning that kind of got messed up. Adding on to that, I was about to say, how are we going to encode text? So I like cats. How do we do this? And that's where it left off. Also, just want to note, my Spanish is a lot worse than I originally thought. So please mind that. All right, anyways, I'll go ahead and stitch this onto the beginning of the video. So recording. So yeah, one-hot encoding. What you do is we're going to say our vocab size is 3. So vocab size is equal to 3, which is just this. It's just all the known words all the words we have. So vocab is 3. It's I like cats. Our vocab would be I like and cats. So you represent this as a vector, where the index represents the word in the order of the word, the index of the word. So in this case, that would be index 0, be index 1, and that would be index 2, and then you would put a 1 there. So this vector would be 1, 0, 0, and then like would be represented as 0, 1, 0, and then cats would be 0, 0, 1, 0, 0, 1, and so on. So you can represent I like cats, the sentence I like cats, as a matrix, like you do with everything in machine learning. So you can represent it as a matrix that is S is equal to 3, and it'll be an S by E matrix. Actually, in this case, it would be S by V. S by V matrix, which is a 3, I guess it's 3 by 3. I don't actually like that.
It's going to be diagonal?
Yeah, in this case, it would be a diagonal matrix. I'm going to add another term so that it's not. So I'm going to increase our vocab size to 5. 2 extra terms that are just there that we're not using, just so that it doesn't look like a square matrix. So these would just be filled with zeros. All right, that's better. So then this would be a 3 by 5 matrix. And then this would be, or a 5 by 3, whatever, however you want to represent it. 0, 1, 0, 0, 0, and 0, 0, 1, 0, 0. So then this first vector would represent the word I. This second vector would be like, and this third vector would be cats. So that's how you represent this in a matrix form. But if we look at the original linear layer, it can only extract features from the vector itself whenever you give it that information. Like it's only good for extracting features from a vector. So to get text information, or to kind of encode the text information, we can use something called a recurrent neural network, which is what this thing was, which is what attention kind of tried to fix, and we'll go into the problems in a sec. But say I have this module, and I'm not going to go into exactly how the module works. If you want to know more, it's called recurrent neural networks. And say this module, I'm going to represent this by a three-part matrix again, or a 3-part vector again, because it's easy for me to draw. And this represents I, so it would be 1, 0, 0. And this goes into this module block thing, and then it outputs some hidden vector, which is arbitrary to us, but it's information that it's encoding about the word I. And then we do this again for the word like. So we throw this through. And what it does is it takes information from H, but it also takes information from like. So it's kind of embedding this information into one vector as you're feeding it through this module. So we keep feeding it through. So this gives us a new output. So this would be H1, this would be H2. So you feed I through the module, and then it outputs H1, which is just the hidden representation so far. You feed H1 and like into this module thing, and then it outputs H2. And then you do this again for, or this is module, and this module is the same. It's the same for everything. So it's not a different thing. It's not a different set of weights. So we'll feed cats in here, 0, 0, 1, and this outputs another hidden representation, H3. So then we can decode this. What's going on over there? So then we can decode this, and then we can output I like cats in Spanish, which is me gusta gatos. So M, and then we output the first. So in this case, it'll output a distribution for what it believes the next word will be. go ahead and turn this
Is
on.
the output limited to the dictionary that you started with?
The outputs limit, so there's two dictionaries. There's the dictionary that we have here, the English dictionary, and then there's the Spanish dictionary, which will be over here. So let's call, so the English will be 0, I, 1, like, and 3, and 2, cats. And then the Spanish will be 0, so those are the indices. Actually, I'm gonna change this up a little bit. Gusta, 1, me, 2, apples, and then yeah, so on. Actually, I'll go ahead and make this a little bit more interesting. Add some arbitrary words in there that we're not going to use. So what this does is it outputs a distribution over all the words. So how likely does it think each word is going to be? So this will be a 5-part vector. So we want it to predict me, which is 1. So it'll probably have a high probability for that. Let me move this down. That's better. So we can just visualize the matrix or the distribution like so, just like that, where we have the weight on here. So if we discretize this, then this distribution represents how likely it thinks each word in here is according to the indices. So
you drew it as a continuous distribution intentionally, though, right?
I did not. It's a discrete distribution. That's why I discretized it. Yeah, it's discrete because it's a vector. So that'll be Gusta. So it doesn't think Gusta is very high, and then the second part in the vector would be me, and so on, according to the indices here. So we sample the distribution. So we get the word me because that's the highest peak. But the sampling adds a little bit of randomness. So we have a chance of getting whatever that word is, yul. So we have a chance of getting that as well. And that adds a little randomness to it by sampling instead of just taking the max value. So then we keep going and we keep decoding. So now we have H4. So it keeps changing H as it goes, and H is just a hidden representation. So H3 right here will encode everything we want to input, or the input sentence, and then beyond there it encodes the input sentence along with what it's currently decoded, which would be, this would be me up here. And then you keep doing this over and over again. So then this word would be Gusta, and they would just output another distribution just like that. And one of the problems with this, there's a couple problems with this. One of them is it's sequential by nature and it takes forever to generate a sentence, or at least to train a sentence, because you have to feed each word in there independently, into this module independently, and since it's sequential, there's no way of getting around that. And then you have to decode each word independently of each other, which takes forever if you're doing a sequence that's very long.
And if you want to train it, just like the normal ways we use backpropagation, if you guys don't know what that is, that's okay.
I'll just show them how the gradients
Yeah, but it's just gradient descent.
Yeah.
I was going to ask how the decoding terminates.
Okay. So whenever it reaches, so it'll generate some special token, which I denote as end, as an end token. So it'll generate an end token, which is just, I'll add it to the vocab. It'll be 5, and this will be end. So it'll generate this.
Oh, so it still samples for the termination.
Mm-hmm. It does. So it has a chance of generating something stupid.
The translation might not be like the same number of words or whatever.
Yeah, it can vary. It can be any number. Of course, you can always cut it off, but that's besides the point. And the gradients, so the way you train this is you want it to output a distribution that is a one-hot distribution. So you want it to output, in this case, it'll be a vector that's 0, 1, and so on, more zeros, because if you remember, me was in position 1.
Does it mean that you fed it or you encoded an end token as well?
Yeah, so that's part of the, no, so you don't, I mean, you can, there's no, In this case, it doesn't really matter.
Okay.
But yeah, it knows when to stop whenever you reach an end token. This isn't the attention mechanism though. So that's what I'm just going over this brief, or just kind of broadly. And you want it to output this distribution that looks like that. And it gave us a distribution that looks like that. So you want it to have 100% probability of being me, of being this word right here. In reality, it's not going to be that. It's going to be really high. And that's how you train it. One of the problems with training is the gradients have to flow through this module M. And they compound on each other whenever you're computing the gradient. So this can lead to what's called exploding or vanishing gradients. Exploding gradients is where the gradient gets massive, then you can't store that number anymore, so it reaches infinity and your stuff breaks and you're sad. And then you can also reach vanishing gradient, or you can also go into vanishing gradients, which either leads to a gradient that's not accurate or one that's so small that it just starts breaking everything like infinity. So that's one of the problems that's another problem with a recurrent neural network. And since the gradients have to go through this module over and over and over again, that's a big problem. So that's what was done before this, before attention is all you need.
And one thing to add with that is because you're it's called backpropagation through time. So you're backpropagating for each thing in your sequence. So the problem with that is that because the gradients have a tendency to vanish, basically the stuff earlier in your sequence isn't going to have an effect on your output the further you get.
Oh.
So it cannot encode. It has a really tough time with very long sequences.
Adding on to that, there's a reason for that. So remember, H is a vector. And this vector is a set size. You can only do so much to a vector to encode. You can only encode so much information to a vector. So this H3 essentially has to encode all information of the input sequence. And I like cats. They could probably do a pretty good job of that. But if you have a sequence length that's, say, 2,000 words, it's not going to be able to do that. And whenever you're decoding, it still has to keep encoding that information. So it won't be able to remember what happened earlier. And at least it'll lose some of that information. And that's a big problem with recurrent neural networks. So they propose this. There's a lot going on here. They propose what they call a transformer, which has attention in it. And attention is the main reason why we're going over this paper, because it's so universal. It's in everything. It's in computer vision. It's in machine translation, which is what they do here, English to Spanish or whatever. It's in audio. It's literally everywhere. So I'm going to go through the attention mechanism first, because that's like the main part of this paper, but there's still so much more about this paper that's amazing. Like the transformer architecture itself is still like used everywhere. Like even computer vision has adopted the attention, norm, feed forward, norm, and then you just stack these over and over again. But let's just go into attention, and then we can go into like how the transformer works from there. All right. So what attention does is it has, so given this matrix, given this sequence of tokens, let me draw it out. I like cats. So given this sequence, you're going to create three different, let me draw the matrix. So I'm going to represent this as a matrix that's of shape S equals 3, or of shape S, which is the sequence length. In this case, it would be 3. So S is equal to 3 by E. And E is some arbitrary encoding. It's some arbitrary encoding length. So each vector is encoded using a linear layer that I showed at the very beginning. So you take the one-hot vector, you throw it through a feed-forward or linear layer, and then you encode it to some arbitrary dimension, and you can do some nonlinearities and stuff. It's just so that you can get it to some dimensionality smaller than the vocab size that you can easily work with. Because the vocab size, in reality, is probably going to be tens of thousands, hundreds of thousands of words, or something like that. So you can't do anything with that, because you've got to put that in a matrix. That's not happening. So we encode this into a matrix it's a square matrix S by E. And then you throw these through a feed forward layer. So feed forward. So you encode this to 3 separate matrices, and this will be the queries. We'll call these queries, we'll call these keys, and we'll call these values. So you encode this to 3 feed forward layers, you throw this through 3 feed forward layers to get 3 output matrices, queries, keys, and values. And these are, I'm going to make them the same shape here to make it easy.
So is E a 2-dimensional?
E can be anything. E is any size. It doesn't matter.
So for I like cats, it would be a 1-dimensional vector, right? Or wait, no.
No,
No, never mind.
it would look like that, and then
Oh, okay.
I don't know. It would be some number of, it would be some vector size for each of these. I'm stacking them up like this. That makes it easy. So this would be 3 by some arbitrary dimension. So this will be S by E, and we're just linearly transforming along the E dimension. So it's kind of changing the vectors in some way to help it, just to help it represent it in some different way. It's just to separate the queries, the keys, and the values from each other so that we don't have the same matrix. Let me finish drawing these matrices. Okay. Now for the fun part, the queries times keys matrix.
Oh, you're showing the projections. Okay.
Yeah, no, that's just
I was
linearly
confused
projecting.
by the cube case. I was like, should you put because there's 3 separate projections.
Yeah, no, these are each
Yeah.
separate. Yeah. So what we do is we multiply the queries by the keys, and I'll show you what that looks like or what that represents in a second. But you compute the inner product between the queries and the keys. So you kind of find the similarities between and you do it along the E dimension. So this will be an S by S matrix. So you compute this matrix at sequence length by sequence length, and you do it to find relationships among all tokens in the sequence. Let me draw this out. So in this case, it'll be a 3 by 3 matrix. So it'll look like this. And I'll actually draw something else over here. So say I have this. So I have the sequence I like cats, and I'm representing each vector as just this circle, and they each output a vector. So each of these will be a vector, and that's what the queries are. So these are the query vectors. So those are the queries, and then you output the key vectors. Oh, sorry, these are the keys. It doesn't really matter, but the metaphor works better this way. So it looks like that. And then these are the queries. And what you do is you find the inner product between all of these vectors. So this would represent I. This would be the output encoding for I. And it would find the inner product. It would take the inner product just like a linear layer does. Well, it's similar to a linear layer, except these are computed on the fly, the queries and the keys. But you compute the inner product between I and every other token. And this will output a distribution that, once you normalize it, it outputs a distribution that'll look like the similarity between the vectors. So if you look at these two right here, that's very similar because they're both I. So that'll be a really high similarity value. And you compute that through dot product. These two, this vector and this vector, have like a 90 degrees, so that would be 0. So this is the relationship between I and I. This is the relationship between I and like. And this is the relationship between I and cats. And I just drew random vectors, so this actually doesn't mean anything. So you output this distribution according to the similarity between them. And what this is kind of saying is the keys are showing off what information do each of these words have. And the queries are kind of like, what information am I looking for to build some sort of encoding? And that's what this similarity represents. And it looks, I think it looks better in matrix form. So it's an S by S matrix, so it'd be I like cats by I like cats. So it'll be like cats. And then we can kind of make a heat map out of this to represent how similar the words are. So this diagonal,
Correlation matrix.
Not exactly.
Okay.
it's a similarity
Yeah.
matrix. So so let me draw it
Diagonal
out.
will be 1.
No.
Oh.
It could
It'll
be.
be high, but
Yeah.
it can't be 1 because that distribution you're getting for each word, the similarity one word has to all the other words. We put a softmax function on it, so that is the sum of all those probabilities will be equal to 1.
So
Oh, okay.
yeah. So
it
each.
has other bounds,
Mhm.
Yeah.
like probability.
So after you compute this matrix, you actually feed this through a softmax. So I'm gonna act like we already did that, and each of these right here is an independent distribution.
As the sum of each row is 1.
Yeah, the sum of each row is 1. It's between 0 and 1, and adds up to 1. So it's just a normal old distribution. So if we look at this, the word I probably correlates high with I. And then you have like and cats. I don't know. We probably doesn't correlate high with those. Like probably correlates high with itself. What am I? What is doing the liking? I is doing the liking. So it's probably pretty high. I'm not an English major, so if I get this wrong, it's not my fault. And then like, what am I liking? I'm liking cats. So it'll probably have a high value there. Cats, I don't know. Maybe it has some low value here. Doesn't really matter. But it's a similarity between the vectors. What I have on the right side, the vector looking things, and what I have on the left side, the similarity matrix, they don't align. I just drew those independently of each other. So this represents the distribution. That's the similarity between the words. And then this is how you are going to reweight the sequence. So the new representation of I will be a distribution that's just itself because there's nothing else that it's really looking for, that the query's kind of looked for. The distribution for like will probably look something like this, maybe like that. And then the distribution for cats will look something like, that'll be 0, so be 0, a little bit, it's a triangle, and then very high for that. So this is the distribution for how the information is going to flow from the original keys, showing off what information is in each of the words, to the queries, what information is it looking for. And this can form it's like a fully connected graph, so it can form some pretty strong, it can encode really strong information. For example, maybe a query would correlate high with, with like in the sequence. But of course, it's arbitrary because it's a neural network. And then you reweight the sequence based off that. And then this, let me reweight it. So that'll be the output. It's E by S. So you just multiply these together and you get an output. And you multiply along the S dimension. So you're multiplying this S by S matrix here by the values along the S dimension. And that way you are getting information, between all of the items in the sequence. So remember, the linear layer got information between items in the encoding space. This gets information between the sequence. And I don't know if y'all, or does that kind of make sense in a way? Because it's very confusing at first how you're mixing this information. It's a routing of information that's dynamic, because you have a linear layer that's not dynamic, but these are all learned. So it's a dynamic routing of information. And I mean that's the basic concept of attention, and you just do this over and over again. Is that
a good way I saw of visualizing or like thinking about?
Yeah, there's that one blog. Is that what you're thinking of?
Oh, I was gonna say like a good way of thinking about like queries about keys and values. That I saw was that like you can think of the query as like a YouTube query, like when you're going on YouTube and you want to look something up, you type in like a query into the search bar. The keys are like some tags on the videos that might pop up, and then the values are the actual videos that pop up. That's kind of like a good a way to think about it, because in the paper they don't really explain it. So that's kind of a good way to think about it.
it's a good way?
Kind of want to think
Honestly, I don't think it's that important because really,
It
that's
really
just,
isn't.
that's
It's very
intuition
arbitrary.
That they try
Yeah.
to attach to it, but really it's just a bunch of matrix multiplications.
Yeah.
What's really happening?
For some reason, it works.
What's really happening is this, and the reason why it works so well is because you're finding relationships between the sequence. Like you have, it's a very easy thing to make work, or it's a very easy thing to make work well because you're finding relationships between everything to itself. So how related is the sequence to itself? Let me find information that way, and that's such an easy way to do it.
Values. I mean, I see keys and I see queries on the screen, but I don't see values.
The value is over here. You just
It's by the values.
What are
That's
the
your
values?
new.
What are
the value.
mean? Like
That's
a word,
an output.
Yeah, it's so you don't even need to feed them through a feed forward layer. The values can actually be the original input. So you can reweight the original input according to the distribution that's saying what information do I want from each value. So this distribution, or this distribution right here, the distribution for I, is kind of saying what information do I want? I want a bunch of information from I and nothing from everything else. The middle vector is saying what information do I want to represent like, and it wants some information from I, some information from cats, and a lot of information from like.
When you say information, this is expressed in probabilities?
It's expressed in weights. So this vector right here is technically a probability distribution, but the distribution itself is the weights that you're weighting the values by.
And where the order matters in particular, right? Like these are basically ordered weights. This is what
Yeah, like
that index means a lot.
because this is a like that's why they're labeled down here. So the index isn't arbitrary.
So basically what you're doing, right, is you compute these weights through using attention, and then you take those weights, and your new representation for the word is like
Well, in this
like
that.
like basically is a combination of all the other words.
In
That's
this,
basically what you're doing in your
in-
sequence.
yeah. In this case, the new representation for like would be a little bit of I, a little bit of cats, and a lot of like. So, and then the new representation for I, since it's a distribution that's 1, 0, 0, it'll be all information from I. And when I say information, I just mean a vector times a weight.
So unlike the first example, the linear model that you showed earlier, this doesn't have to consider an entire dictionary?
There's the linear layer for
So like in the last example, you know,
In
you
this part.
started adding like arbitrary words that like
in this part.
Yeah. So, you know, it thinks of this in terms of like, I like cats, like those are indexed
Mhm.
based on some dictionary, right?
Yeah.
But in order for this to work, you have to have the whole dictionary, right? Is that true in this attention?
So it is, and it's a case. This is the case in both of them. So what you do is you have
It's
this.
an embedding matrix.
Yeah.
That's just
So you're gonna have a huge sparse matrix.
Well, you initially do. So you have this huge sparse matrix 0, 0, 0, 1, 0, 0, 0, 0. Or sorry, yeah, vector. You have this massive vector of shape v by 1, so it's a vector, and v is the vocab size. And then you encode this using some linear transformations into some smaller vector that's of shape e. And that's why I had e up here. This is where e is less than v. So you take this massive vocabulary, and since vocabulary is going to be massive, you shrink it down using, you kind of shrink the vector down using linear feed forward layers. So it would be a linear combination of the input in some way, and you use it's an encoding matrix, embedding matrix. And it's kind of like a lookup table in a way. Since you have these zeros, you can kind of have a table where like you kind of have a lookup table, and then it selects the vector that it's looking for. So this will be the vector for like. And then since you do a matrix multiplication, it kind of selects this vector and then nothing else because it has zeros there. And then this vector, this will be a V by E matrix, and you multiply by that, and then you get this value. You get this embedding for the vector. And then you feed those through. So what I showed up here, you actually wouldn't feed that through because you would have a massive vocabulary. You would embed it and then you feed it through. So this is working with the embeddings, not the vocabulary size. And we haven't got to how this predicts stuff yet. We just got to the main part of it. So you're relating the sequence to itself. That's what this is doing. And you're finding relationships between the sequence and itself in here. And that's the tension. Yeah.
So you scroll down a little bit. That row where it's like, is that storing its like similarity to every other word, or?
No. So this is
That
a
is
look.
some vector representation for the word that we have.
It's like all the words in the dictionary have been like plotted into like
Smaller dimensional space.
let's just say a 300 dimensional space, and like in theory maybe similar words are like should be grouped together, but you know.
Yeah, it's arbitrary in this case. So you multiply it by this massive matrix. So you multiply the input vector by this massive matrix, and it's essentially a lookup table where it just selects one of the vectors because it's sparse. It's
Okay,
sparse.
so it's
So
like-
it'll select that.
A, B, C, or D is going to take you to like another vector that has a smaller list of words?
No, the vector is A, B, C, D, E.
Okay.
So I guess A, B, C, D, E, D.
It's not as massive as our one-hot encoded vocabulary, so we can actually work with them. Because you can imagine if we work with those one-hot encoded vectors, our number of it would just be, like, you just wouldn't be able to do anything.
Well, I guess what I was imagining was like if you had an actual dictionary and you just numbered the entries in the dictionary.
Yeah, and it's just like that because you number the entries and then you take the meaning of that word and you encode it. And instead of it being encoded to words, you encode it to some arbitrary numbers that it knows of that we do not.
If you
And-
number it like that, then like.
I mean, that's
tomorrow
basically
we'll
what this matrix
Find
is doing.
relations between words that are alphabetically similar, and we don't want that, so.
Oh, so it's not ordered.
Yeah,
You
it's not
want that, like, that embedded matrix in theory should, like, either use pre-trained embeddings for like, learning over time through backpropagation, but it should encode some meaningful representation of the words, right? So like what Sophic was talking about, similar words should be grouped together. There should be like relationships, like, I guess, logical representations of words that we would like in that matrix. We want it to be useful.
So you can just think of it as a smaller encoding space
Yeah.
where vectors may be similar to each other. It's some internal representation that it comes up with, and it's consistent for all. It's the same for every vector, or it's consistent. So this vector for like is not going to change unless the network changes it itself. So after the network's done training, it'll always be the same. So the vector for like is always going to be the vector for like. It's unique.
I was gonna ask. So for this, you don't need to do any back propagation like you need to do for the recurrent neural network, correct? Am I thinking about that correctly?
We need to do. It's similar, and we're going to get to that.
Matrix or this attention operation?
The attention off.
No, we're going to get to that. So
Oh,
the
we're
Yeah.
gonna make layers. Don't worry.
Okay.
so
okay.
what you do in a transformer
You
is
can't
you're
get
like,
away from back propagation.
yeah, you can't. Actually, you got forward.
Okay.
I'm kidding. All right. So, anyways, if y'all good with attention, kind of, it's a very abstract idea, but it's just finding relationships between the words and the words itself. That's all it's doing. So that's what, and they show it off right here.
This is impossible to have a functional model that could be done right.
Oh, there's no way.
It's going to perform poorly. if
This
it's
has
not
like
it's-
100. Okay, so GPT-3 has 175 billion parameters.
Damn.
Try to change those by hand. That's not.
We actually did presentation on it.
I just mean, if you tried to like manually write something like this for I like cats, it's not going to work because it's going to perform poorly with such a small dictionary.
It could work
You
with
could-
just
you could-
itself, but it would
I'm
just
pretty
work by
sure
itself.
Somebody tried doing it for like handwritten digits.
Yeah.
You can like manually do it, but like that's basically as big as like a model that you're gonna get
It's
detecting handwritten.
one of the things about this is you need a lot of data. You need a ton of data. So this network architecture takes more data than it usually requires more data than other architectures. So if you give it a little bit of data like that, it won't learn anything. Yeah, it's really good. but it's really good at if it has a lot of data. And it in a way, it kind of remembers things. It kind of remembers the data, which we're finding with GPT-3. So anyways, that's the attention parts. I'll get into the masked later, and then I will get into this part later, just in a sec. So you have this input embedding. This would be I like cats. And you are going to embed it to some matrix. So this matrix will be of shape, just like I showed below, S by E. And then you're going to positional encode it. So I'm gonna make this kind of simple, how you do positional encoding. But one of the problems with attention is it works on unordered sets. So it doesn't know the position of everything. Like the position of I and the position of like and the position of cats, it doesn't mean anything. You can feed I like cats through, and technically it'll be the same as like cats I, and they're the same because it doesn't have positional information. It doesn't know the positions of these words. So to get around that, they add these vectors that are they add positional encoding, and to represent that, yeah, just sine and cosine. So you can make, I'm just gonna draw sine, but you can make, let me draw out some sine waves, my awesome looking sine waves that are of doubling frequency. So that'll be F, 2F, and 3F. So they each have a higher frequency. And if, say we have our vector, say we wanna have a 3-dimensional vector, then we would need 3 cosine waves. So say this embedding size is equal to 3, E is equal to 3. And then we need 3 different sine waves of varying frequency. And if I sample this uniformly, like so, then I can look at then I can make a vector for each of these with the values of the sine waves. So I don't know what that is, but let's just say it's 0. Let's say that is 1. Let's say that is 5.
0.5.
Oh, 0.5. Like what? We got varying frequency, not varying amplitude. All right. So and then you encode this vector. I don't know. I'm just gonna change it a little bit. 0.4.
You said you're sampling them uniformly,
Mhm.
but okay, no, sorry. Go ahead.
Yeah. So
To the negative one.
-1.
No, I said e to the -1.
Oh yeah, e to the I sine pi or whatever that is.
Yeah,
I sine
e to the
theta.
I over
Euler's formula.
Oh,
I to
yeah.
I.
Yeah. I'll show
We're
you.
not doing magic.
Yeah, we're not worrying about
Don't
that.
worry,
We're worrying
don't
about the
worry.
sampling
No
part.
complex plane here. Don't worry about it.
1, and 0.5. All right, so you have a unique representation for each of these vectors. So I guess S is also equal to 3. So what you do is you create these sine waves, and then you sample them uniformly for each of the for each vector in the input. So we have a sequence of length S. You sample uniformly S times. So, and then you add these vectors to the original sequence. So this would be the vector representation of I. This would be the vector representation of like, and this would be the vector representation of cats. And then you add these together, and then you get a new output vector for each of these. That is the joint. It's a combination of the input embeddings, but also the positional encodings.
Seems extremely convoluted.
Extremely what?
Convoluted.
Yeah.
Actually, it's kind of stupid, in my opinion.
I think it's
The
stupid
first
too.
time we saw this, like
And
our
just-
professor was talking about it, it's like so arbitrary. It feels like they just kind of pulled it out of nowhere.
Can
And
you
it
just
just sort of
index them
works.
or something?
Can you what?
You could just like index them, like increase the vector length and like have the header row be the location of the word.
Well, this is indexing them. You have to find a way to index them in a meaningful way, because I could just add 0, 1, 2, 3
Yeah.
to them.
That's what I was thinking.
The problem with that is the scale, and it's just
Yeah.
and you have more meaning if you have a vector of values than a scalar.
Mhm.
In this case, we have a vector that's the same size. You can encode a lot more information into that.
Wait, so this uniform sampling thing, you just uniformly sample.
The sine waves. So you have this, you have sine waves
So
of,
like what interval would you, or is that like a predetermined?
so this will be,
It's probably arbitrary.
it's not arbitrary. In this case, it's not arbitrary.
So it's like a.
It's you sample s times in between there's a min value and a max value that you have. So the min value is say 0, and the max value is some value at which the sine waves start repeating their pattern. You sample s times between that. They have a formula for
So
this.
it's just a uniform distribution between the
Oh.
min and the max. So you sample it whatever n many times in between.
Well, s many times.
Same thing.
Well, I called it s here. So.
They're the same.
No, n is batch size.
Whatever. N, K, S, who cares?
So you sample s times and you get s different frequency vectors that are different. I always questioned why add them when you can concatenate them.
By S, do you mean the size of the embedding or the size of our vocabulary?
The size of the
The
sequence.
size of the sequence.
Memory
Yeah,
by
you
adding
s-
them, right?
Hmm?
Why not concatenate them?
Yeah,
Just
I-
single memory?
Yeah, probably, but I thought maybe it could find its
Wait,
own.
why?
It's arbitrary.
It's arbitrary. Concatenation and addition,
Wait,
it pretty much learns the same thing.
Yeah.
It just does.
It just
Why
does.
the next
Wait,
layer?
why though? Wait, that
It just does.
would be a different operation.
Yeah,
Yeah.
Why the next
machine
layer?
because machine learning. All right. So, anyways, what you do is you take
I know
this.
you're a stats guy, so you probably like care about like understanding why things work.
It-
Yeah,
in dumb learning, that's
that's
not how this works.
If we went into like how it worked exactly, well, we could go into like it more. We could go into it a little deeper, but that would take forever for this.
Trust.
And also, I forgot the formulation of positional encodings. To be honest,
Everyone does, yeah.
because you just take the formula and you.
I mean, you never really do
But it's like the way
positional
things
encoding,
work
you just
is
let
like
it do it for you.
we try something arbitrarily,
And if it works.
and then we try to come up with
So a few years later,
intuition.
somebody
somebody comes up with the reason.
This was made in 2017, and this thing is stuck since today. Yeah, make an attention is all you need paper, and you'll be
Go
famous.
Write a paper on it. Do some
I wonder
research.
if I'm gonna the reason. I'm gonna look on it.
So anyways, you add positional encodings to this so that it knows where each value is. And so you have this matrix, you have the one hot vectors, you feed them through an encoding matrix, so you encode them to some lower dimensional space. Then you add positional encodings. And then we start doing operations on it. So you have the multi-head attention, and you'll notice these 3 parts. So these 3 parts represent the queries. Why is this so big? 10. That's better. So the queries, the keys, and the values, and the positions of these will be important in the decoder. So you have the queries, keys, and values, you compute attention. So it'll take this matrix in, and like we showed before, it does some similarity between the sequence, and then it outputs something of the same length. Add a norm. So a normalization is, they use batch norm in this case. Batch norm will center the distribution at 0.
Wait, don't they use layer norm?
I thought it was batch norm.
I could have sworn they used that.
I mean, whatever. It's some normalization.
It doesn't really matter.
Yeah. So, I mean, whatever. Right? Layer norm normalizes the layer weights, while batch norm normalizes the whole batch. It's just normalization to
It's
help
good
the
for
gradients. Yeah. It's when you see normalization, it's helpful for the stupid gradients that don't like you. And then you add it, which is you add a residual connection, which is also good for the gradients. But in a way, it kind of allows it to change the initial data as opposed to trying to come up with new data from that initial data. At least that's kind of how I think about it. And it also it allows it more freedom to kind of work with this. It just helps it in general. And it's also arbitrary.
Alright, so the explanation they say for using the sign positional encoding, they say we chose this function because we hypothesized it would allow the function or the model to easily learn to attend the relative positions, since for any fixed offset k, PE position plus k can be represented as a linear function of PE position.
All right.
So they
There you
just-
go.
Basically, they
Whatever
guessed.
that means.
They guessed. they were like, okay, this will make it so
Trying to
they're
gaslight-
simple.
trying
And
to
then
gaslight the readers.
Yeah, that's exactly what they're doing. So anyways, you feed it through attention, you normalize it, you add a residual. There's actually a paper on residual connections, which are just found to help in general. It's in everything. Feed forward layers.
ResNet.
Yeah, ResNet. So feed forward
You should call
layers.
this residuals are all you need.
It should be.
I wish.
So then you have this feed forward layer, and what this does is it takes, so multi-head attention works on the sequence. So remember, we have a matrix that's S by E. So attention works on the sequence part, while the feed forward layer works on the encoding part. They work on different parts. The feed forward part is kind of preparing it for the next layer. It's preparing each encoding individually for the next layer. You can think of it that way. So you take the initial encoding. I'm just going to represent it as a single vector. So this will be of shape E. And then you blow it up to shape 4E, to some higher dimensional space. And then you bring it back down. And then you apply a GLU to it. Definitely GLU. No ReLU. We don't care about ReLU. And then you bring it back down to shape E. So you're blowing it up to some massive dimensional space, and then you bring it back down, probably because it's easier to work in higher dimensional spaces. So they blew it, and it's an inverse bottleneck. So you blow it up to some high dimensional space, and then you bring it back down, and that just prepares this encoding for the next layer. That's all the feed forward layer is doing.
As for why they picked the number 4, that is arbitrary.
It is arbitrary. So if we go down here to where they formalized that, right here, you project it once, that's this part. You add the bias, so that's just one feed forward layer. Then you apply ReLU, which is the max between 0 and that encoding. We actually use GLU because it helps the gradients. It doesn't lead to dead neurons or dead weights. And then you project it again to some smaller dimensional space, and that's all it does. It's just preparing it for the next layer. And then you come up with this matrix H. Remember in the initial RNN, how we had a matrix H after we encoded all the words? That's what this part is. So you feed the input embeddings, I like cats, through this n times, a bunch of times. I guess n in this case would be the number of these layers. And then you come up with a matrix H. That is just the encodings for I like cats. Now we need to do this for the outputs. And the outputs use a very similar architecture. So I like cats. We're going to output this one at a time. And actually, let me show you down here how it does it. So now we have this matrix H. That is the encoded representation of H, S by E. And this is the encoded representation of I like cats.
And the S is 3, right?
Right, S would be 3 for that. But it does it's whatever the sequence length is, and E is arbitrary. So we have this matrix H. Actually, I'm gonna draw it out in here. So this will be the encoder. Encoder, and then it'll output. That'll output H. So we have this input embedding, which is I like cats. And then we feed that through the encoder, and then we get the output. So, so anyways, now we need to decode it. Now we need to get Mi Gustagatos from this. So we have so what we do is we start with a token. We start with the start token. So start. And so now our sequence is a 1 by E sequence. So it's S by E, and S is equal to 1. And we feed that through the decoder. And then we also feed the hidden embeddings, which encode I like cats, into the decoder. And then this will output a vector for the next word. And the vector is a probability distribution over our vocab. So this is where the vocab comes in. This is where the output vocab comes in. And this will be some distribution over all the vocabulary words, whatever that looks like. And then we sample it, and we get the next word, which will be me.
So not only can it give you an output, it can give you a confidence in the output.
It does.
I mean, I guess usually like the user shit that I see like doesn't usually tell you, but Somebody could calculate it, right?
Well, it does tell you. And if you look at G,
Like, when I use Google Translate, does it say like, hey, we're pretty sure about this one?
it doesn't show you, but in the background it does.
In the background.
Yeah, in the background you're sampling it. So it always has you sample according to its confidence. So this will output a word, and the word will be me. So now we have a sequence that's start me. And we take this sequence, and then we form a new matrix that is of shape 2 by E. So S is equal to 2. So we have start and me now after generating me, and then we throw this through the decoder, and the hidden state stays the same, along with the hidden state. And then this outputs another vector, and this vector represents what is the next word going to be. So it'll be some different distribution. Wow, what a good distribution. And then we take that, we sample it. So then we get the word gusta. So we sample this. That looks like a good sample right there. And that'll be the word gusta. So it puts it in the sequence, and so on. You do this over and over and over again until you reach the end token. So it'll be me gusta. So S will be 3 this time. You feed it through. You get gatos. You feed that through. You get an end token. So it'll be gatos, and then end. So it's just like the RNN in the last case, except the encoder does this all in one step, while the decoder does this in the number of steps needed to generate the output sequence. So let's go into how the decoder kind of looks like. So remember, the decoder just outputs a distribution for each word. And if you're curious, remember how attention outputs so the decoder and the encoder all output a sequence of shape S by E. If you're curious, you always take the last vector. So say we had start me gusta. So this would be 3 vectors. That would go in there. And then you always take the last vector, and the last vector represents is what you project linearly to the distribution. So then this would be the distribution for the next word. Because you have to take this matrix, and then you have to somehow find the next value. I think they also had a way where you do a linear combination of all these, and they found that just taking the last one worked. And you can think of it as condensing all the information needed for the distribution into one vector, and then that's where you get your output distribution. And then you just do that over and over again until you get your output. So the decoder is very similar to the encoder. And if you want, I can go into masked multi-head attention. I'm a big fan of that. But the way this works is you have the start token, and then so on, however many it generates. Start me gusta. So we'll just say that's our sequence for now. So that'll be an S by E matrix. You add positional encoding, and then you feed it through here. And then you get your queries, keys, and values for your attention. So then this is your attention mechanism. You do your add and norm, and then this is the special part of the special part of the decoder, in which you have take the hidden representation, and you find a way to encode that you find a way to encode this to the decoded representation. So what you do is you only take the queries and the keys from the hidden state, so from this state. So the hidden state goes here, and you make the queries and the keys, and then so this will form your S by S matrix. So the hidden state will form your S by S matrix. So you're finding relationships among the initial hidden state, and then you're multiplying that by the values, which is the decoded state here. So you're weighing the output sequence by the encoded input sequence for this one, and then for the first one, you're just finding relationships among the input sequence. So this is a way to somehow give information to the output sequence from the input sequence to tell it what was the input sequence. And you do this over and over again. You do this n times, this block n times. So it'll be the attention to itself, attention to the input matrix. So attention to itself, attention to the input matrix, to the input words, and then you output that and then eventually you will get your you'll get your distribution for your output. And yeah, y'all want me to kind of talk about masked multi-head attention? Y'all are curious about that? I can do that. All right. So one of the ways you can like one of the problems I said earlier is that the decoder takes a long time to create the decoder takes a long time to decode information, to generate words. You can parallelize this. So the encoder is already one operation, or one set of operations where you feed the whole sequence through, but you can actually parallelize the decoder during training. So specifically during training, but training is you want to parallelize as much stuff as possible. So we have the queries. This will be an S by E. Queries, and you have the keys. Keys, S by E. And the values don't matter for this. And then you do the queries times the keys, and you get this vector, or you get this matrix, that's S by S. So if we look at this matrix, if I draw the diagram again, it represents the similarity between I like cats and I like cats. I guess, actually, no. It's me gusta gatos, because you don't use this in the input. Me gusta gatos. So this is your similarity matrix, which is 3 by 3. And if you look at the way this matrix works, you can see that me has information of everything. So say we were to give it the word me by itself. Say we were to give the decoder the word me by itself. So this is just a vector that you're inputting. This is just a vector that's of shape E. And if you look at the similarity matrix, it'll look like, actually I'll draw it in blue. So if you look at the similarity matrix, whenever you just send me through the decoder, you'll see it's just a box. It's just a 1 by 1 matrix where it represents the similarity to itself. So it represents the similarity of the me query to the me key. And we can actually do that in the similarity matrix for the whole entire sequence by masking it. So notice how me can attend to, and by attend I mean just do some sort of do the attention mechanism to whatever it's attending to. So notice how me can attend to future words. So me can look ahead, and it has information for gusta, and it has information for gatos. We don't want that. So what you can do.
So those gusta and gatos are like blank right now.
Right now they're not. So in this case they are, but in this case we fed the whole sequence through.
Oh. Okay.
But we can make them blank by leveraging softmax. So what you can do is you can make these negative infinity, and then make this, so you add a triangular matrix to this, which is just negative infinities in the top triangle. And then they'll become zeros because, yeah.
So, no, I was going to ask why you weren't going to do it as upper triangle, but then I realized that the diagonals would go 1, so never mind.
Yeah, so this would be a 1 in this case, because it has to attend to something. Like it has to have a distribution of something. Yeah. So this will actually become a distribution that's 1, 0, 0. And then this will be, I don't know, A, B, 0, and this will be, I don't know, C, D, E, some values. Whenever you add this to that. I'm going to remove that because I prefer doing this. So now you can see that whenever we feed the sequence me gusta gatos, me cannot look at anything in the future. Gusta cannot look at anything in the future, and then gatos can because it doesn't have anything in the future. And you may think, why don't we do that? Can't me look at the future here? This me right here it does not, because this is the representation of me. Gusta can look at the representation of me, and so can Gusta can look at the representation of Gusta. So it only matters about the vectors going this way, not about them going this way. And then whenever you multiply this by the values, it keeps this property. So remember, it'll just be a reweighting of this. So me keeps the property where it just looks at itself. Gusta looks at the property where it just looks at me and Gusta. And Gatos looks at has the property where it can look at anything. And that's how this is what the mask is. So you can mask it by just adding a matrix, a triangular matrix of negative infinities in the upper triangle, like that. So you just add that, and then it won't be able to attend to the future. And if we go up here, it's only doing it here. So whenever you're decoding a sequence, I like cats, and you give this to a machine learning algorithm, it knows the whole entire sequence. So you don't need masked multi-head attention here. It knows what you want to encode. But you need it here because it needs to decode. So it'll start with start, then it'll go with me, then it'll go Gusta. So you need the upper triangle mask here. And then you have this part right here. And this part does not need it as well. It's not masked because the attention mechanism only works on the queries and the keys. That's how the relationships form between the sequence. But the sequence is only between the input. So you don't need to mask it because we know everything about the input. So that's why there's no masked attention here. And the feed forward part, you don't need any masking there because it only looks at representations in the E part. So it only looks at representations of each vector independently. So if you just mask this part, you can get you can send a whole sequence through and get predictions for each part of the sequence. And remember how it outputs a matrix that's of shape S by E. So S is equal to 3 in this case. You can treat each of these. So you can treat this as the prediction. Remember how we just took the last output? Well, in this case, you can take every output and you can treat this as the prediction for the next word. So this would be the vector me, and this would be the output vector me, and you can take that, linearly project it here, get the distribution, and then the distribution will be the distribution for the next word, and then you can formulate the loss over that. And then this vector right here will be the vector for Gusta, and you can do the same with that. So we essentially took this operation that would take S times, where S is the output sequence length, and we did it in one forward pass. And you can only do this during training, but like that speeds things up a lot. And so you only need 2 forward methods. You only need to feed it forward once here and once here. And that's one of the biggest, it's one of the best parts about transformers. Does that masking make sense to y'all? Yeah. And you can there's other types of masking, but that's what they use here. You can actually do like padding masking as well, where if you have a pad token, you can just mask that out so that the sequence doesn't attend to that. Multi-head attention. So multi-head attention is saying, instead of just having one attention mechanism, why don't I have multiple at the same layer? So instead of having one here, I just add a bunch of them. And the way you do that is you split the I'll go ahead and draw this part out. So you have this matrix, S by E, or I'm going to draw it the other way, E by S, because it makes it easier. And then you split this into multiple parts. So this will be, I'm going to say we have 4 heads. So this will be E over 4 by S, and so on. So you have 4 of these that are E over 4. And you're just splitting the original query keys and values by that. So this is, I'll just call this
so
queries.
E's the embedding matrix.
Right, E's the embedding.
So you're sending a fourth of the embedding vector.
So you split it. You
split the embedding vector.
Yeah,
in 4 parts.
Yeah.
Okay.
You're splitting it, and then you send these independently through attention. Now I'm going to name these attention 1, and so on, and then attention 4. And each of these attentions have different weights. And then you get representation, which is O. That's also E by 4. So you send these queries, keys, and values through the attention, and then you get this output. And then what you do is you concatenate them together. So then you have your original shape, that's E by S. Oh, sorry, I said E by 4. E by S, my bad. So you essentially split it up. You do attention on all the split matrices. You combine them back together, and then you send this through a feed-forward layer just so that it can find relationships among the new embeddings. And that's what multi-head attention does. And you can think of it as, in a way, like you can think of it as finding, say, the pronouns, and each head finds something differently. Say head 1 finds the verbs in a sequence. Say head 2 finds the pronouns in a sequence. And it does that all at the same layer, which is much better than doing it in sequential layers. So you're essentially making it wider as opposed to deeper, making it with the multiple heads. And that's what multi-head attention does. Of course it's arbitrary, but they find that it helps. At least having 2 heads helps, but they usually use 8. So that's multi-head attention. And I think that's pretty much it. I don't think, oh yeah, one important thing. This will be real quick. This one side note is the downside to attention, as I've just been talking it up right now. The downside to attention is it takes so long. So you're computing this S by S matrix, and if you have a sequence that's say 2048, I think there's some transformers out there that have that. So if you have a sequence that's 2048 tokens long, this matrix right here will be 2048 squared. That's how many entries it'll have. And you have to store that all in memory, and then you have to do computations on that. So that's where you run into problems. And it's not just space-wise, it's also time-wise. It's quadratically, so attention is quadratic in terms of time and space. So in space it takes up, and in time it takes to compute the matrix. So that's one of the downsides to it, and you can use sparsity to make that better. But
Space is not a big deal because...
Well, not for like Google.
Yeah. I mean, in general, right? Like with how far GPUs have come, like it's...
I would say that
the
it's still
bigger
not.
concern, I think, is...
No, because like, we're limited to 2048, I guess, but
Yeah.
make that 5,000, then like,
That's great.
Yeah, if you make it any size that's like GPT, that's just gonna be massive.
Yeah.
It's a massive
their
matrix.
size.
I think it's 2040. I think it's
It's
2048.
2048.
So
They use some sparse attention, but...
there's
even
so
that-
if you
even
look
that's
at the
still n root n, like it's still not that great.
if you look at any of the attention mechanisms, none of them
Very expensive.
there has been no
It's 96, by the way.
96.
No,
What's
96 blocks, but the sequence size is 2048.
Yeah, it's not 96. You can
Yeah.
put way more than 96.
That's
in
the
there.
number of decoders.
Also, just to point out, a token is not a word. A token is actually a split up word. So if I had, I don't know, what's a good word I can split up? Attention. That's a good word. So I split this into 2 parts. So I split it into I guess I could split it into down there. So you can split it into 2 parts, atten and shun. So this part is 1 token and this part's another token. So the sequence length actually holds less. But you can think of like the ending TION or the ending ION. It's going to appear in multiple words, so your vocab is smaller, and the representation for ION will be the same for every ION. And you can think like that's pretty reasonable. Same for attention. It probably won't show up again, but ION will. So
also like GPT does like text processing and like splits up words based on like predetermined stuff.
yeah, it's called WordPiece, and it was introduced
yeah.
it was introduced before BERT, but BERT I think kind of popularized it. But it's called WordPiece, and you split up the words, and you make the vocab size smaller, and it encodes a better representation. Because if I had attention and attentions with an S, they're 2 separate words, but with this they're not. You have attention, and then you have ION, and then you probably have S at the end. So they would be the same, except one would have a vector S next to it. So and that's one of the drawbacks to attention. You have quadratic complexity. It's bad. and there hasn't been a way to solve it. So if y'all can solve it, y'all would make billions of dollars. Actually, y'all would probably make a research paper, and then Google would make billions of dollars. Somebody would make billions off of it, as you can see here. Yeah, you probably won't, but you may not even get the credit for it, but you can say you did it. I guess let's just look at the results real quick. So, I mean, if we look at the results for this, they claim that it is a much smaller amount of flops, and maybe it probably was then, but that's actually a lot larger. That's actually massive now. It's gonna be massive now. So it actually has more flops than most other architectures out there. But then it was better, I suppose. And then you can see the results. I mean, they're pretty good. This
like GNMT at this point was state of the art. And that paper came out like a year before this.
Yeah.
They just destroyed it.
GMT destroyed it, as you can see, and then it's just gone. It's gone up from there.
Yeah.
It's insane how good this is, and you can use this for. Yeah, like I said, you can use this for everything. And GPT in this case it's a decoder. So, yeah, I think it's just a decoder.
It is.
So you just have this part right here. Since you're not doing a translation, you don't need to encode anything with GPT. So you just have this. You just stack these blocks. And what is it? 96.
I mean, GPT can do translation though.
Yeah, but it doesn't use it. It can, but that's just
No,
built
I mean,
into the
it's
weights.
more like, I think they found that if you're doing anything where, like if you want just for like few shot learning, they just found that just pure decoders tend to work better.
Yeah,
And
and
encoder is useful if you want to do something with embeddings or.
well, it makes sense too. And there's a reason why you use the decoder is because you can parallelize it.
Yeah.
You can't parallelize this. I mean, and if you do, you come up with a decoder.
Yeah.
So you just use the decoder for GPT. And actually, I could show you the results for that GPT had. Let me show you. I just want to bring that up because it's interesting. Random. Let me find my GPT. Here we go. Hmm? Yeah, I can show.
We presented on that paper, so.
We'll show everyone else. Do you remember what page it's on?
Dude, it's like there's like 10
wait,
pages.
what are you talking about?
Which
There's
is
like
the-
60 pages.
Yeah.
Oh yeah, this is one of my favorite graphs. I love this graph. So they claim that it does good at arithmetic when it's clearly just learning when it's clearly just remembering the
I
so
love how proud they are of it.
oh yeah, they're like really proud of this. Sorry, this is a side note, but I just think it's hilarious. They're like, so they're like, so you got this addition and you got this subtraction, and look at this. It's insane. Look at the bars. It's almost 100% accuracy. Three digit. Oh, it's almost 100% accuracy. And then you look at like 2 digit, or you look at 5 digit, and it's like, wait a sec.
Yo, who cares if you do 2-digit addition?
No. You don't understand. It's clearly generalizing. And then you look at 5 digit. Yeah.
So like we're like a step away from general intelligence with this.
Yeah, exactly. Clearly. Look at this. It can almost do 5. It can almost do 5-digit addition. It's 20%.
It's like, it's better.
It only
It's
took
so much better.
It only took a billion examples to learn.
No, bro, this paper is like.
This
What are we
Like their whole
looking at?
claim,
What is this?
their whole
What is
claim
this?
is like, hey, we're not going to change the architecture at all. We're just going to make it bigger.
Yeah.
Look, it works.
They actually, some of the data that they tested on was,
There was data.
this is the GPT paper. If you want to read the 63 pages, you can.
Oh, wait.
I did.
Wait, this is the GPT paper?
Yeah.
GPT, yeah.
But anyway, sorry, I wanted to show you that
Why
funny
do they
thing.
have that graph in there?
Because they're showing how great they are.
Yeah.
It's like, no.
Well, actually, so they did that, and like they had an example where they're showing few-shot learning, where you basically give GPT-3 a few examples, and one of them was like, what's 9 times 5 plus 4 or something, right? And like the first one was like
We made that up.
32, and then they're like, oh, here's
Oh,
the
no,
example.
we did that.
Yeah.
We made that up.
We did that.
So it's really ripped up from the paper.
No.
No, we did
I actually love how they say it's, I forget what they said exactly, but they basically said it generalized on math, and it did
But
not.
It does math so bad.
Well, yeah, clearly.
I have an example of it, like,
I mean, it does few shot learning, but it doesn't do zero shot learning.
It doesn't know math, and they claim
yeah,
it
at
kind of
At the
does.
last meeting, I did like
Pretty bad.
Yeah, the whole like Danny DeVito thing, remember? I ran it and I told it like, you're wrong. And it's like, oh yeah, I'm sorry, I'm wrong. It's this.
Yeah,
It's like,
yeah.
And I was like, no, I'm like, no, it's not that. And I gave it the answer. And then it's like, oh, okay, I see now. So then I asked it again and it got it right. So then I opened another window, asked the same question, and it got it wrong again. And I'm like, what are you doing? Like, just get it right.
So yeah, I mean that's the transformer. Y'all got any questions about it? Pretty interesting architecture, right? Love it. Well, I mean that's it. Yeah, it was.
Wow, that's attention.
That's attention.
Kept me attention.
Thanks for your attention.